Good afternoon and welcome to Advanced NMR Spectroscopy course. So today I'll continue with what I was telling in the last lecture. So this is about recording of 1D NMR spectrum. What are the different parameters we set, how we set those parameters. So in the last class, I talked about the T1 measurement. Okay, so what is T1? T1 is nothing but it is a longitudinal relaxation time constant. Okay, so longitudinal means it happens in the Z axis only. Suppose if you see this is your and so the movement of magnetization. So this is the equilibrium magnetization. So this is your mz, the movement of magnetization along the Z axis. So that is the thing. Then that is the thing we have to observe. Okay, so for that we have to monitor the magnitude of mz along the Z axis only. So for that the pulse sequence is first we will give you a 180-degree x pulse. X pulse means we'll give the B1 field from the x prime axis, and then we'll give some delay time, that tau. So once you give that 180-degree, what will happen? This magnetization will come to minus Z axis. Okay. It will move to minus Z axis. And now you are giving a delay time of tau. Tau is nothing but it is a variable time. Okay. So each experiment it will vary. So let us say in the you have given some time. So during that time, so you see if you give 180-degree pulse, what will happen? You will have the magnetization will move to now minus Z. Okay. Minus Z, and then you are giving a delay time of tau. So during that time, let us say it will shrink by. So let us say if you give a time and then you will see there is a shrinking of this. It depends on. It can go even to plus Z axis also. Depends on how much time you have given, or it can become even zero also. Okay. So that we will discuss. So let us say that its magnitude will decrease. But as you know that you cannot detect this when the magnetization along the Z axis. So you have to detect it by bringing, because your detector is only in the XY plane. So you have, so that's why after that time tau you are giving a 90-degree pulse. So if you give a 90-degree pulse, if it is in the minus Z, it will again you are giving a X pulse. So it will reach in here. Okay. Okay. So you will detect the magnetization, although the signal phase will be different, but you will be able to detect it. Okay. So this during this tau period, there is a relaxation. The relaxation is happening by T1 relaxation. Okay. So this is the main aim. So let us see how we do it. So that only I have shown you. So you started with a Z component magnetization, equilibrium Z component magnetization. You gave a 180-degree pulse that brought the magnetization to the minus Z axis. Now you are giving a relaxation. That if let us say if the relaxation tau is less than, now there are three times I have shown you. One is Tz is a time, and then there could be, it could be less than Tz, it could be more than Tz. Okay, so let us say the time is less than Tz. Tz means when the magnetization becomes zero. Okay, so we will not check it. So the magnetization becomes zero. So let us see if it is less than that. What will that means? You can see the magnitude had reduced, but still it is in the minus Z axis. Okay. Now you give a 90-degree pulse, so it will bring to the minus Y axis, and you acquire the FID. And then if you do a Fourier transform, you will, because it is now in the minus Y axis, so you get a negative peak. Now when this tau, the delay time is more than Tz. At that time, you'll see the magnetization will now reach to the plus Z axis. So if you now give a 90-degree pulse, it will bring it to plus Y, right? And you look FID, and then if you do the Fourier transform, you get a positive signal. Okay, but when it is at tau, the delay time, if it is exactly matching with the 0, then you will see that there is no signal. Okay, now let us see how this helps in determination of the T1. Okay, so now let us see that. So last class I told how I have derived this equation, the equation governing this variation of mz, okay, with time is given here. Mz is equal to m0 into 1 minus 2 exponential minus t by t1. This, and I also explained in the last class why you are putting t, because if you see that when you are inverting m first it has to go from minus m to 0, and from minus m0 to 0, and then from 0 to plus m0. So which is equivalent to 2 times of m0 relaxation. It is not 1 time, because it is from minus m0 to 0 and 0 to plus m0. So that's why this 2 is coming. Okay. Now, if you see that what we are doing now, this is the pulse sequence. We are giving 180 degree, and this is a variable time. Okay, and then we are giving a 90-degree pulse that I already told you, and then you are collecting the FID. Okay, so what you will see when at the, let us say if the tau is very small, so you will see, or let us say tau is 0. So if you give a 180-degree pulse and subsequently 90-degree, you will see your magnetization is coming to minus m0, is the full magnetization is at the minus, along the minus Z. And if you do a 90 degrees, you get along the minus Y, and that's why the phase of the signal is minus Y. Okay. And then if you keep on increasing the tau, you will see that slowly the system is now undergoing the relaxation, and then you will see that at a particular time you will see there is no peak. That's why I was telling you it is a Tj, and then you will see the peaks becoming positive. Okay, so that is a kind of, see, you are doing a series of experiments actually, and then you are plotting mz versus t. Okay, now you see that your Tz is, in this particular case, it is at 5.5 seconds. Okay, and similarly the mz0, okay, is 1.27. Okay, so that is what is the magnitude of the mz, or magnitude of the signal at 0 time when tau is equal to 0. Okay, so so let us see how this equation modifies when tau is equal to tau z, or your magnetization becomes 0. So mz is becoming 0 when you at tau z or tz, what I am telling, this mz will be equal to 0. So if you put mz equal to 0, then you will see that as m0 is not equal to 0, you will see this is becoming equal to 0. And last class I told you that, so you can see that if you simplify the equation, now your T1 is equal to Tz, means that at the time, this point, Tz, the crossing point, by 0.693. And for this particular example, you will see that T1 is equal to Tz is nothing but 5.5 seconds divided by 0.693. So it is coming 7.936. That means your T1 relaxation or time constant is 7.936. So what is the consequence of this? Okay. Now let us see. So we saw only one peak. Okay. But when you see in your spectra, you see your spectrum contains large number of peaks. So and each group of nuclei will have their own T1 values. All of them will not have the same T1 value. As you can see in this spectra, you see at around 6.25. Okay, almost all these peaks, either they are at T0 or they have started becoming positive. But still you see that this group of protons still negative. Okay, so this is becoming somewhere here between these two. Somewhere it will become, because still here it is negative and here it is positive. So somewhere you will see around between 1.25 to 2.5, you will see this is becoming 0. Okay, so you must consider that the longest T1 for a whole spectrum, if you consider, so if you consider the T1 you want to use for further experiment, you have to use the group of protons whose T1 is the longest. Okay, okay, that's why you should not select only one peak. You should select the whole spectrum and see which group of proton is taking maximum, which is having maximum T1 value, and you select that for your to use that parameter for your other experiments. Okay, so here I have shown you what is the effect of T1. So T1, what do you mean by T1? So depending on your T1, your delay time is fixed, DE. If you remember, if you are using a 90-degree pulse, you have to use 5 T1 delay between two successive AKITs. Okay, and that's why I told you that if you do not want to use that because it requires, now for this you will require about 40 seconds delay between two successive pulse. Okay, so that is called the pulse repetition rate, and if you want to avoid that, you can use optimize the angle, that is called the Ernst angle, and I have told you how to do that. Okay, now here I have shown a case. This is a furoic acid, say furan 2-carboxylic acid. If you see this spectrum, okay, is recorded using a total number of scans. Both samples are dissolved in DMA, so this acts as a solvent. Number of scans are 64. Under the exact same condition they are recorded, but in one case the delay between two pulses are given 30 seconds, whereas in this case delay is 0. Okay, and the spectra, you can see that when the delay is 0, you can see the magnitude of the peak or intensity of the peak are reduced. Okay, and here also you can see when the delay is more, the intensities are more. Not only that, you can see that because these are the three protons, so they are coming in 3 different positions, and you see their integrations are also showing is to 1 is to 1 is to 1. But if it is when the delay is 0, you see their integrations are also different. Okay, so because they have a different relaxation time. Okay, what I mean to say that in this particular case the spectra got saturated. Okay, because of you are not giving any delay, so slowly the spectrum is getting saturated and there is no further absorption. So that's why the T1 is very important, and this is very important parameter if you want to decide the Ernst angle. Okay. Now I'll come to the another relaxation, that is called the T2 relaxation, and this is also called the transverse relaxation. Okay, okay, and this determine how fast the phase coherence. So actually it happens in the XY plane. Once you bring the magnetization into the XY plane, and then the phase coherence between the spins is lost. Okay, that is nothing but your T2 relaxation. Okay. So although you will see that when you bring it to, there is a change, phase coherence is lost, means one spin is getting converted to alpha, then other is getting converted to beta. So the overall population of alpha beta state is not changing, but their coherence or the phase is changing. So the effective magnetization in the XY plane is decreasing. Okay, by this way. So that means your signal is also getting decreased. Okay, so in this process there is no change in the energy of the system, but the spins are getting randomizing. So that's why it is called an entropic process. Whereas T1, if you see, T1 is a enthalpic process, because there the nucleus is getting transferring its energy to the lattice, and then that's why it is going back to the original equilibrium position, and that's why it is called the enthalpic process. Okay, now you can see that as soon as you bring the magnetization in the XY plane, okay, you see that, and you give time for that, you will see that the magnetization gets, because they are losing now their phase. Okay, so due to this phase, the effective, see, if you see the effective magnetization due to this, it is this, is your M, that is you are detecting M effect. This is your, but if you see in this case, it will be reduced because it has got now spread. So this is reducing. Here there will be further reduction. Here there will be further, and in these cases probably it will be 0. Okay, so you will not get any signal. So that's why, if let us say you are putting the detector along the y-axis, if the magnetization does not decay due to this phase incoherence, you will see a continuous signal. Okay, there is no change in the signal intensity. the detector. But if you see that as it is spreading, it is fanning out all this magnetization, the detected signal is getting reduced over the time. Although the period is remaining same, but the magnetization or the intensity is decaying, and from that one can find out what is E, that the decaying constant is e to the power minus t by t2, or it is following a time constant of 1 by t2. Okay, so now if you do mathematically, it becomes like that: mxy at particular time will be mxy 0 exponential minus t by t2. Okay, so and if you plot this, you will get a slope, a linear line, a straight line, and slope will give you 1 by t2. Okay, so that you can find out very easily. Now, the importance of T2 is that it decides the line width of your signal. Okay, if the T2 is shorter, you will have the broader signals. Okay, and if it is only pure, and you will get the new. Okay, so if you let us say you have a signal like this. Okay, so this delta nu is delta nu is equal to 1 by pi t2. Okay. Now, if it is, see, if your this is true when there is your magnetic field is extremely homogeneous. Okay, then only this the spread at half height, the frequency spread at half height gives you the T2. It's a very simple way to measure the T2. But in a real case, this is not that true. So there are actually spin relaxation. You have to know the mechanism. So how the relaxation happens? It is because of the nearby oscillating magnetic or electric fields. Okay, which are changing or reducing or augmenting the external magnetic field slightly, and so automatically that is making the some nuclei will precess faster and some will precess slower. So that's why the fanning out is happening. Okay, so this fanning out of the individual spin vectors resulting in decrease in the mxy magnetization, and that is nothing but they are losing the phase coherence. That is, so the main issue is not that. So if it is the only mechanism, then one can find out the T2 just by measuring the signal width at half height. But the main issue is that so you have that, but there is a main field inhomogeneity. Okay, so if there is a main field inhomogeneity, because of that you will see some parts of the samples, okay, leading some parts will be moving at slightly higher frequencies, some part will be moving at lower frequencies. Okay, so what you will see this, then the relaxation time will be called the effective relaxation time. Okay, so it is now a mixture of the oscillating magnetic electric fields as well as the main field inhomogeneity, and that combined thing is called T2 star. And always the T2 star is less than T2. So automatically, if you cannot detect T2 by measuring the signal wave. So let us see how to do that. That means somehow you have to avoid this dephasing or the magnetic field. How we have to ignore the magnetic field inhomogeneity. Let us see how to do that. Okay, so let us see before going to that. Let us see how to measure the T2 star. Okay, so T2 star, as I told you that now what you are getting is not T2, but it is due to T2 star. So that's why it is coming from the T2 star is nothing but 1 by nu half. So the half width is here, and what is the delta nu spread here, you can find out. So it is very simple. Another way is to that you can record the FID. Okay, so and you can see this is like a first order your decay curve, and you see T half is equal to 0.693 T2 star. Okay, so if you see the T half is nothing but the where the signal intensity is becoming half of that. So in this particular case, you see that at 0.33 time unit, the signal intensity is becoming half. So you can you can modify these equations. So T2 star is equal to T half by 0.693. For this, how we'll find out? So here it will be T2 star is equal to 0.33 by 0.693. Now this is time unit. Okay, so normally this time unit is in let us say in second, so it will be 0.33 by 0.698 second. So you will get your and you will see it will be less than 1 second. Okay, so this is now T2 star. Now for measuring T2, what you have to do is that you have to avoid the magnetic avoid the outcome of magnetic non-homogeneity. Let us see how to do that. Okay. So what I mean to say that effective transverse relaxation time. Okay, as T2 is greater than T2 star, so T2 cannot be determined from the normal FID data. You cannot detect because normal FID data is giving you only T2 star. Okay, now as we know, the transverse means it is happening in the XY plane, so you have to design a pulse sequence for that experiment. So the technique is called a spin echo experiment. So spin echo experiment will be you will see that this is a pulse sequence you will be see very frequently used in many 2D experiments. So you should know what is happening during this spin echo experiment. Okay, so what we are using a 90-degree X pulse, and then you are giving a delay time, a tau, that is variable, and then you are giving a 180 x. X means we are using the x-axis. This will be actually x prime. Okay, because we are using the rotating plane. So these are we are giving a pulse along the x-axis, 90-degree pulse, followed by a delay tau, followed by a 180-degree pulse, and then you are giving another same. These two delays are same. Okay. For each experiment, these two delays are same. Okay. Now, if you go do a new experiment, you will see you will have a different tau value. Will be tau 1, and this will also be tau 1. Then you will have a tau 2, then you will have a tau 2. Okay. And then you will acquire the FID. Okay. Now, let us see. So now you have at the equilibrium condition, the aim is along the Z axis, and then you are giving a 90-degree X pulse. Okay. X pulse, or this is your B1 field. Okay. So now what will happen? What will make? It will bring the magnetization. So to the y-axis. Okay. Now you are turning of the B1. Okay. And then, so what will happen? Your magnetic moments that comprise of M begin to dephase due to one is due to the field inhomogeneity, and another is decay due to T2 relaxation. But we would want to remove this effect. So how to do that? So that if we remove this effect, we can get the effect of T2 relaxation. So how we are doing that? Okay, so this now see this now because of this B0 field non-homogeneity, you will see that once you bring into y axis and you are giving a delay of tau because of magnetic field non-homogeneity, you will see that some spins are fanning out. So some spins are moving slowly. This side is a slow, this side fast. Okay. And then you are giving a 180-degree pulse. Again, X pulse. So what you do, it will move and bring the thing here. So there will be you are giving along the x-axis, the pulse. So it will come from the it will bring here, and that is now become here. So you will have again you the fast moving vectors are this side, and slow moving vectors are that side. So this will move now. So and then again you are giving a tau time. So this will move and this will move this direction, and again they will coincide at the y-axis. But during this time there is also normal T2 relaxation. So whatever decrease happening in this magnetization is purely due to the spin relaxation. Okay, so see, this will not be equal to this, because that has been reduced now. So we have, by this process, we have reduced the magnetic field non-homogeneity. Okay, so you are getting only the magnitude reduction of this will totally depend only on the spin relaxation. Okay, so now thing I have already told you. So that thing only I have told. So the only effect of transverse relaxation due to T2 will be operative, that will decrease the MXY. That only I told in the. Okay, so the FID curve now governed by the true spin relaxation. Okay, now it will not be by T2 star, and so automatically you will see that now this whatever FID you are generating is solely due to T2, not due to, it is T2 star. Okay, so and from that whatever I told for T2 star can be applicable here, and you can find out the T2. Okay, so that explains your T2 relaxation. And if you remember, this is a curve I told you about how the this relaxation times depends on the correlation time. Okay. Okay, so if you see that T1, I told you that T1 also for small molecule also T1 is large, and for large molecule also T1 is large, and there is a minimum. Okay, when that correlation time is matching with the meshing frequency or the precessional frequency of that nuclei, you will see a minimum T1. Okay, but if you see that T2 is continuously decreasing as the correlation time is increasing. Okay, so correlation time is nothing but how much time it is taking to rotate by 1 radian, okay, or to move one distance of 1 diameter. Okay, so if at log Tc is increasing, that means the molecular size is increasing. So that means if the size of the molecule increases, you will have a shorter T2. So shorter T2 means you will have a broader line. So that's why if you go for macromolecules like proteins and other macromolecules, you will see the lines are quite broad because of this correlation time effect. Okay, how that affects the T2. Now we'll discuss about what is called spin decoupling. Okay, so what I have discussed you in my earlier lecture 7 and 8, that what is spin coupling first. Let us understand what is spin coupling first. Okay, because I have already told, still I will tell you that suppose if you take this molecule, this is the isobutanol, and you will see that that all these groups of protons, they are coming at different place due to the chemical shift, but not only they are not coming as a single line, but you see them as various kind of multiplet structure. For example, these two methyls, they are chemically equivalent and they are coupled to only one proton, so that's why they are appearing as a doublet, and I told you why they should be doublet, I have explained. Similarly, this CH is connected to these 6 protons and this CH2, and they are coupling constants are very similar. That's why you are getting a total 9 lines. Okay. Similarly, this CH2 is coming as a triplet that is connected, that is coupled to this hydrogen as well as this hydrogen, and coupling constants are very close. Similarly, the OH is also coming triplet. So that I have explained to you. So I told that this is happening because of the neighboring nuclei. Okay. Now let us see little more about that. In fact, if you remember that when recording carbon-13 spectrum also, if you record a carbon-13 spectrum also, so that was only for hydrogen, but when we record a carbon-13 and you will see normal carbon-13, no decoupling, you will see this carbon is coming, although here you can see quartet type, but each line of this quartet is again splitted into triplet. If you do a very good, if you record the spectrum in with good resolution, you will see that each line is again a triplet. Okay, similarly, you can see that this quartet, which is coming due to this methyl, is also coming as a each line will be quartet and then it is coupled to this hydrogen, so doublet of quartet. Similarly, this CH, this will be your CH2. This CH2 will be coupled to this CH3 and this CH3, so it will be a doublet of. This will be make it triplet. This will make it doublet. This will make it quartet. So it will be a very complex thing. Okay. Although here you can see only because this has been recorded in a very poor resolution. That's why. Okay, you cannot see, or deliberately it has been done. The line broadening is given up to 5 Hz. Okay, so that you will not see the coupling constant below 5 Hz. So that you will see only the coupling constant above 5 Hz. Okay. So why this happens? Why this line split? That also I have explained to you. That I have told you. So let us say for you have a CH, okay, which is interacting with another CH. Let us say HA and HB. Okay, so what is, let us say we are seeing the spectra of HA. So what it is saying that you have HB can have alpha spin and beta spin, and they have the equal population. So you may say that equal, yes, they are almost equal. Okay, I will not say, because there will be a slight excess of alpha. That's why you are able to see NMR. But for coupling, that we can consider they are equal. So what it will see, that HA will see CHB alpha in one configuration, and another configuration it will see HA CHB in beta. Okay, so what you will see essentially, so you will see, so there will be a combination like this. Okay, so this will be your alpha, this will be your beta. So, and automatically, so they will not have the same energy, so their interaction will be different, and you will see that your HA will split into 2 lines, and that is called nothing but JHA HB. Similarly, HB will also split into a doublet if there is no other proton to couple with this. Similarly, this is a case you can see clearly when you have 2 identical nuclei with spin half. Okay, so one can see that they can have both alpha alpha. One can be beta, another can be alpha. This is alpha, this is beta, and both can be. And if you see the their population distribution, it will be, if you consider this could be a one combination, but there are 2 possible combinations, and this is one combination. That's why you see when a proton or a nuclei is interacting with 2 equivalent protons or nuclei with spin half, you will see a triplet, and the intensity ratio of those 3 lines will be 1:2, 2:1. I think I have elaborately discussed during the spin coupling. Still, I repeated it here. Now, what is spin decoupling? Okay, so now what we saw, that this coupling is coming because you have the 2 clear-cut energy levels of the neighboring, let us say in this case, protons, alpha or beta, and these spin states are interacting with your target nuclei. These spin magnetic moments are actually interacting, so that the field experienced by this target nucleus is slightly more or slightly less. Okay, but when you are now in spin decoupling, what you do, you selectively irradiate this neighboring proton or a group of neighboring proton with a strong radio frequency at that particular frequency. So what it will do, if you irradiate a group of proton with another radio frequency, those nuclei will now start flipping very fast from one state to another, and that situation is called saturation. Okay, so what you will see, the target nuclei will now feel an average field due to this rapid spin exchange. So if you see an average field, so automatically it will appear as at a average position. Okay, it is not now seeing 2 spins separately, seeing a average. Okay, so this is called the spin-pin decoupling. We'll see how to do it. So now when these two sets of nuclei, what we are doing are same, let us say proton-proton, we call this is a homonuclear decoupling. But sometimes you can do with other nuclei like proton-carbon or proton phosphorus, proton fluorine, and in those cases we call that is, let us say it is a proton decoupled carbon 13, we call this is a heteronuclear decoupling, and the nucleus which you are actually decoupling, thus the nuclei which you are saturating is put inside the bracket. For proton-proton it is not needed, but when it is a heteronuclear you have to mention it. It is possible, you can do record a carbon 13 with 19 fluorine decoupling. Okay, so that's why it is needed. Okay, so here I have shown you a complex molecule and how the spectra got simplified, or how the various protons are identified. Now you consider okay, now let us see that there are many protons, okay, many groups of protons, and okay, so now this and all these protons have been identified. Depending on the number given here, you can see they have been identified and they have been mentioned here in the spectrum. Okay, so you can see that this methyl is coming as a singlet. Okay, whereas this methyl is coming as a doublet because you have a hydrogen here. Okay, so it is coming as a doublet. Okay. Similarly, now the proton, this H7, is coming at this position. Okay, so now if you do a decoupling, or if you saturate this proton, okay, this proton, what you will see that because this H7 is coupled to these two protons by a allylic coupling, although it is a allylic coupling, a long range coupling. Okay, if you remember, this is a 1, 2, 3, it's a 4-bond coupling. If you 4J, if you remember, but it happens. I have told you that. So this is a 4J coupling. It happens. Okay, so you will see this allylic coupling. So this coupling, if you saturate this, you will see the coupling to these two protons have disappeared, and you can see it's simplified. You see this picture. So when you are irradiating at proton at 7, you see there is a simplification. So the coupling is gone because it is seeing a average field, because this proton 7 is now changing the spins very fast. Okay, and see the 7 is also connected to H6. So this H6 is now, you see, it was a weak doublet, the coupling constant was large, and you see now that also now become singlet. Okay, and this H7 is connected to H8, and you see now that coupling due to that has gone. Okay, so it has simplified, but the H8 is coupled to some other protons. Okay, so those coupling will still be there. Okay, it is only that proton which you are irradiating, that coupling will vanish. Now you see that if you irradiate the proton 1, this hydrogen, this one, this hydrogen, so you see that the coupling, so the coupling of these to this will disappear, and then you will see that these two also, because there is a allylic coupling, and you can see there is a change. Okay, you can see that if you irradiate that, you have now seen that your these two protons, and sorry, these 4 lines and these 4 lines are simplified as a doublet, because now these two will couple to each other, only that coupling constant remains. You see these two doublets are of equally spaced now. Okay, whereas doublet of doublet structure is formed. So this is the way one can identify all the protons, or you can correlate the chemical shifts. Okay, so I have shown here the how it is done. This is process called double resonance technique. Okay, so this is done with a second transmitter. So you have now 2 transmitter coils in the XY plane. One is giving the V1 field for the whole spectrum, and you are giving a very selective field B2, that is selective to that group of protons which you want to saturate or bring into the double resonance. Okay, so your radio frequency nu1 or that is giving the B1 field, is giving you the spectra, and then you are using another radio frequency field of nu2 that is designated as B2, and that is a very selective frequency where you want to do the irradiation. Okay, so what you have to do, this is so you have to first give a 90-degree pulse. So if you give a, so initially let us consider the protons. The magnetization is here, which is coupled to those two protons, or a proton. So there will be two. One will be slightly moving slightly slower, another will be moving slightly faster by this rate, plus minus half J. J is the coupling constant. Okay. Now you have given a 90-degree pulse. You brought into the y-dash axis, and now you are giving a small time, so that you can see now when you give a time, because of this because of the they are coupled to each other, so the one will be moving slowly and other will be moving fast, but this will be equal. The slow moving, the relative the motion will be same, one in clockwise, another will be in anti-clockwise. Okay, now let us say you are giving the second field, okay, B2. Okay, so if you give B2, what it will do? It will take away that magnetization from y-axis, and that will keep on rotating. So this is your field, so it will keep on rotating. That I have shown here. So it will keep on rotating along the around the x-axis. So what will happen if it is rotating? Means it is changing its position from alpha to beta alpha to very fast. Okay. So effectively the coupling will go. So that means this will be frozen. Okay. So this magnetization vectors will be frozen in position. So if it is frozen, that means you will have the effective magnetization, and that can be detected. And see, that is being detected, and you are getting a one signal. Okay. So previously it was giving two signal, now it will give you one signal. Now what happens to the frequency where you do the irradiation? You will see how, because that's why if you remember the earlier I was showing a beat pattern. So either you will see a beat pattern or a kind of negative broad and negative non-symmetrical peak. Okay, so this is the way that we have irradiated at this position. Okay, or at this position. Okay, so it depends on, sometime you will see this beat position, sometime you will see, so this beat position is you see mostly when the frequency is not exactly matching. Okay, exactly not matching, whereas this will see when the frequency is, because there could be a very little bit difference in when you are considering a, let us say, multiplet, it will be difficult to select exactly the frequency position. Okay, but anyway, it does not matter. It gives you the result. Whether in spectra you see these or these, you know that where you have done the irradiation. Okay. Now let us see in case of heteronuclear spin decoupling. Okay. So here again the same spectrum I am showing. It is for this 2-chlorobutane. You see all these things. This is you will see the triplet of quartet, doublet of quartet, doublet of triplet of quartet, and doublet of triplet of quartet, depending on the which carbon. Because here you can see that, as I have told you, the coupling constant can go beyond up to 1,3 bond. Okay, up to 3 bonds. So you are seeing, if you consider those things, you will see that this CH3 is this carbon is coupled to these 3 hydrogens plus these 2 hydrogens. This carbon is coupled to these 2 hydrogens, this hydrogen, these 3 hydrogens, and this is like that. Okay. Okay. Now if you do a decoupling of all the hydrogens, okay, so the coupling due to hydrogen will disappear. Okay. Because that you will not see in case of homonuclear decoupling, because we are doing hydrogen, you can see in the same spectra which you have decoupled. But here we are decoupling all the protons, and protons come in a totally different frequency than the carbon. Okay, so that's why you see all carbons are coming as a separate peak. And I will tell you in the next class why the intensities are different, because that is happening due to the nuclear Oberhauser effect. So I will cover that in the next class. Okay, so now all 4 carbons are coming at 4 different positions with 4 chemical shift values. Okay, so this is called the heteronuclear spin decoupling. Let us see how it happens. I have taken a simple case when, let us say, chloroform. So you have only 1 carbon and 1 hydrogen. Okay, so if you consider that, So the carbon will actually see that hydrogen in two positions, alpha and beta. Okay, so automatically due to that there will be a splitting of its line with a coupling constant value of half 1j CH. Okay. Okay, so now what you do, now we are giving the same pulse sequence. If you remember, now we are giving a 90-degree carbon pulse. So we are bringing carbon into the y-axis. Okay, and then you see because of this coupling, so this vector will be split into two vectors, and one will be moving anti-clockwise, other will be moving clockwise with the same speed. Okay, because that is arising due to the coupling constant. Okay, because they will have now a offset, and that offset will be equal. Okay, now if you are doing the acquisition, you will get the FID, and if you do a Fourier transform, you will get a normal proton couple carbon-13 spectrum of chloroform. Okay, so you got how the coupling is rising. Okay, so now let us say we want to do a decoupling. Okay, so whatever we have done for proton so now we'll be seeing what we want to do for proton decoupled spectrum. So whatever I have done for proton coupled spectrum, so up to that everything is fine. Now what we are up to before, until we collect the FID, all the steps are same. That means we are giving a 90-degree pulse, and you saw the vectors are moving into opposite direction with the same frequency, with the offset. Okay, now just before the acquisition started, the sample was irradiated with a strong continuous B2 field. Now this B2 field is not in carbon. B2 field is set to the proton frequencies because we are irradiating proton. Okay, so your B2 channel is coming from and we are using a very strong B2 field because you have to, because so that all protons will be decoupled. Okay, we are not doing a very selective decoupling here, like in case of your homonuclear decoupling. Okay, here we are removing all proton couplings. Okay, that's why we need a very strong B2 field so that all proton couplings will be lost. Okay. So this broadband irradiation of proton nuclei causes the net magnetization due to proton nuclei. So I told you when you are doing that, when you are giving B2, so the B2 will be rotating around the X prime axis. Okay, so the coupling to carbon will be lost because it is now rotating in that, and its coupling will be lost. So what you will see that if you do the acquisition now, instead of two lines, now you will see only a FID of a single line, and that is nothing but the average of two lines. It is the same in case of proton decoupling and carbon decoupling. It is same. Proton we are using B2 is in the same proton frequency and very selective. Okay, whereas in carbon decoupled, proton decoupled carbon, you are selecting a very broad band or which can decouple all protons in one shot. Okay. Now, what we saw that if we do a fully decoupled carbon-13, all carbons appear as a singlet. Okay, so it simplified your spectrum, but due to this simplification, certain very important information about the structural analysis is lost. Okay, because we've seen that in carbon coupled spectrum, carbons can have coupling with protons from neighboring carbons, making it very complex to analyze. If you do a good resolved spectra, you will see a complex multiplets are coming. Okay, but suppose if we can turn off the coupling of all protons except those directly attached to carbon, like if let us say if you have a CH3, CH2, CH2 like that. So you will see that this carbon will be coupled to these three hydrogens and also these two hydrogens because up to 3-bond coupling. But suppose if we can turn off these couplings, so you can very clearly say this is it will give you a quartet. So that you can clearly identify that this is CH3. Similarly, this CH2, it is coupled to this CH3 also, the neighboring CH2 also. Okay, so if you can stop those couplings, okay, this coupling and this coupling, then it will come as a triplet. Okay, so let us see how to so that it will simplify. It will tell that how many protons are attached to that carbon, and that process is called off resonance decoupling. Okay. So what you do here? Here this nu2 or the B2 field is not set at the center of the proton spectrum. Okay, you are not, see, in the case of fully decoupled, you put the B2 field, select the B2 at the center of the proton spectrum. Let us say you have a proton spanning from 0 to 10, or your nu2 should be set at 5 ppm, 5 ppm. But here you don't do that. What you do, you select the nu2 offset from that center. The offset will depend on which machine you are using. It can be 1000 to 3000 Hz. Okay. Okay, it depends on the which machine you are using. Okay, so what, by doing this offset, what you are doing is that it will reduce all the coupling constant of protons to carbon. Okay, so all the coupling constant will reduce. So only one bond coupling constant can be seen. Others will be reduced to an extent not to be seen. Okay, they will be less than 1 Hz, so you will not be able to see them, or maybe less than 5.5 Hz. You will not be able to see them, and that will depend on the what offset you are taking. Okay, so that's why I'm telling that this offset range I have given. So you can find out. See, you may have to do a couple of experiments. You may not, in one shot you may not be successful. Okay, you have to choose the correct offset. So that's why, and automatically the coupling constant, now what you will see, the 1J coupling constant, 1JCH will not be the same. Okay, it will be now, it will also be now reduced. What is the reduction? That is called the reduced coupling constant, is nothing but 2 pi the J, the original J value of that original 1JCH. This is the reduced JCH, and delta nu is that offset value what you are taking. Okay, divided by the gyromagnetic ratio and the field strength of B2. This gyromagnetic ratio to be taken in unit of radian per Tesla Hertz. Okay, and B2 field should be taken in Tesla. Okay, so you can tell what will be the reduced field constant, or if you measure the reduced field constant, you can correlate it to the normal coupling constant. Okay, so this is called the off resonance decoupling. Okay, and this is one example I have shown you, that this is if you do a broadband decoupling. So this is a valorolactone. If you see, if you do a normal broadband decoupling, all the carbons come. So this is your carbonyl carbon, and then you can see this will be your CH2O carbon, and then this will be your CH2 carbon. So this carbon, and then the other two carbons, and this is due to your TMS. Okay, so all become a single thing. But now if you do a off resonance decoupling, you can see that this CH2 is coupled only to these two hydrogens. Okay, so they are coming as a triplet. Similarly, this CH2 is also coming as a triplet, and here you can see there are two triplets overlapping. Okay, so there are two triplets overlapping. Okay, so those are due to this one and this one. Okay, and this is due to your TMS methyl quartet. Okay, due to TMS. Okay, so you can very easily characterize the molecule. So using this, so we will discuss with many more example in our special classes which will take after your 2D NMR course is over. Okay, so I stop here. If you have any doubt, you can ask. Okay, so now only your this small part is left. I will finish that in next Monday, same time at 4 to 5. Okay.
In between, next Wednesday we have.
And then this Wednesday only, na? So this coming Wednesday, your 2D NMR course will start. And coming Wednesday and Friday, you will have 2D NMR courses. Okay. But my part, small thing is left. I'll take it on Monday, next Monday.
Okay,
And that is nothing but a nuclear overhauser effect, because I should give you little bit introduction, although it will be very occasionally used in your 2D NMR. Okay. So you learn from there also, but maybe I will give a brief introduction about nuclear overhauser effect and how, and you have already seen how the proton decoupled NMR spectra, carbon-13 spectra is affected due to this. So I'll see how that NOE is useful in stereochemical analysis of organic molecules. Maybe one or two examples I'll try to include. So if you have any doubt, you can ask.
also mentioned that part is from Tuesday onward, Professor Hosu will take 2 classes together. So
Tuesday, Wednesday.
Wednesday.
And the other thing is that Professor Hosur will be taking you this 2D NMR. Okay, so he will take 2 classes. Okay, twice in a week. Okay. Okay, so it will be on Wednesday and Friday. Okay, but I will be taking 1 class on next Monday, so there will not be any coincidence with that. Okay. So if you have any queries, any questions, any doubts, you can ask me now, or you can even send email. Okay, and I also remind you that I have given you some assignments, and that last date is 17th. Okay, so please, those who like to appear for the exam and this thing, they must submit it before 6 p.m. I think I have given the time.
Submit carries marks. So
yeah, that I have told. Yes. All, and I will give you another assignment on next Monday, covering whatever part I have taught. Okay. The last 6-7 lectures. Anything else, Baldi? Okay. And if there is no question, I will stop here, and thank you very much. Okay. So please join on Wednesday at what time? 4 o'clock?
4 o'clock, yes.
Wednesday at 4 o'clock,
4 to 6.
or that class will be from 4 to 6. There will be a break for 10 minutes in between. Okay. So Professor Hosur will be taking your 2D NMR, and I think all of you should attend this class. It will be quite enjoying. Okay. Thank you.